Hi, my name's Brian. In this video, we'll be covering Computing Project 2, including modeling planes, normal vectors, detecting contact, resolving contact, linear interpolation, and what you need to do for this computing project. So when you download the code, this is the first thing you're going to see, as usual, comments. And when you run your code, you're going to see this plot. And if you don't see this plot, something might be wrong with what you downloaded. Make sure that your .m file has the correct title with no parentheses in it, and that your plane is initially set up correctly. So as usual, we're going to clear everything with the clear in CLC command and then define our initial problem data. Here we define our initial conditions so we can start analysis. And then next, this is what's going to change from the last project. We're going to define a plane. So for the in-class problem, what we had was a line that the projectile bounces off of, and that line is defined by the g of x comma y function. And then for the computing project, you're actually going to want to define a three-dimensional set of planes. So you're going to have 6 planes total that you're going to need to define, and you're also going to want to make them general, so you can have it with width, length, and height. The size of the box is going to be able to change on demand. So here you're going to want to define your normal vector, and for the computing project you're going to have to define 6 normal vectors total. So it would be very wise to have MATLAB just compute that for you and then do it for each plane. And again, this is just what we covered in class, where the normal vector is equal to this equation. So then next we have our numerical analysis parameters as usual, and then our dofig commands. And then we have our history array, which you can leave all as is. And then you have the output to the command window, and you can leave this alone as well. Here's where you're going to initialize t to be t0, and then you're going to initialize the output counters, and then you can initialize xold and vold. And this is how the code is initially, and you don't need to change anything. So here's where you use the equation of motion for phase 1, which is projectile motion. So this should look very familiar. You just have your one force, which is gravity. You sum the forces, set that equal to ma, and then you have your equation of motion. Aold is going to be equal to minus g in the E3 direction. So all of this work so far has just been to set up our actual numerical integration, so we can go ahead and start our MATLAB time-stepping algorithm. So in this first part, as usual, we only need to save some of the values. And then in this, we're going to start introducing the idea of energy. So we have the potential energy and kinetic energy, and those are calculated by U, which is potential energy, is equal to mg x dot E3. And the x dot E3 takes the E3 component of the position vector. And then we also have kinetic energy, which is defined as T is equal to half m x dot x dot. So as usual here, we're going to be computing velocity and acceleration with trapezoidal rule. And now we have everything necessary to check if our particle is in impact, which is phase 2. But let's just take a second to look at what's happening so far. So in this problem so far, we've just been in phase 1, which is just projectile motion. So we have some v minus, which is our velocity before impact, and then we have the minus mg. And then suddenly there's some reaction force perpendicular to the plane, which is in the n direction. And then during this instant in time, our equation of motion actually changes. So our equation of motion goes from free fall to minus mg in the E3 plus r n is equal to mx double dot. And then after impact, this is phase 3, we're going to have some velocity afterwards. So we have to resolve contact. So the easiest one to do right now is the one in purple, and we're going to do basically the projection onto the equation of motion, and then we're going to integrate the equation of motion over that instant in time when there's a reaction force. So when you take the first part, that goes to 0, and the second part goes to 0. So after you go through the calculation, you're left with that the velocity in the direction of the plane actually remains the same. So in order to get the velocity in the plane before or after impact, you just have to take the velocity before impact in the direction of the plane. So then next you can do velocity normal to the plane. We come up with a model for impact. So we take this italicized v to be equal to the opposite direction of what it was before, and then we scale it with the coefficient of restitution, which is e, and we take that n component, and that's what that equation means. So this is what the actual MATLAB code for detecting contact for a two-dimensional plane actually looks like. So the equations, we define this Vn because we use it in multiple places, but that's just the velocity before impact in the n direction, so n dot v. And then we have that little v, which I just mentioned, is the scaled velocity after impact. And then we also calculate our energy loss here, which is defined in the CP notes that you can read. And then we define the projection matrix, and that's related to the n vector. And then you bring that all together, and you have the velocity after impact is equal to that italicized v in the n direction plus the projection times the velocity before impact. And then we just go ahead and use an fprintf statement, and that's going to print it to the command window. So this is going to be the most important part of the code that you have to change. You have to take this if statement that only accounts for one plane, and you want to be able to make it account for all of the planes, which is going to be 6 planes for a box. And then we have that if statement, and we're going to basically adjust it to account not only for fnew, but also fnew and fold to make sure that it has just crossed the plane. And that's in the course notes, and you can go ahead and read over that. And then also in the course notes, you want to use linear interpolation to adjust contact time, position, velocity, and acceleration. And that'll make our solution better. These are kind of practical things that you have to worry about when modeling numerically. After we resolve contact, of course, we can update AOLD, VOLD, and XOLD. And that's it for the time-stepping algorithm. And then we have our graphical outputs. So we have our 3D trajectory here, the XYZ components, and then we have our energy. And that's it for this computing project.